So in the next bit of this presentation, the second half, in the first half we looked at some primitive, simple methods for facial recognition. And now what I would like to do is show how we can use the singular value decomposition as a method also to do face recognition. So first of all, I'm going to do a little recap on singular value decomposition, then show how you can use it for face recognition, and finally we're going to wrap up by looking at how actual modern face recognition algorithms, the type that Google, Apple use, work and what is in there. And I'll finally give some pointers to more literature if you're interested to find out more about these techniques. So let's see. The singular value decomposition is a relatively modern matrix decomposition, and MATLAB is one of the most famous software packages in numerical mathematics. It stands for Matrix Laboratory, and basically every data type that you have in MATLAB is a matrix. So if you do multiplication standard, it's matrix multiplication, and it thinks everything is a matrix and a vector. One of the leading people behind MATLAB is Cleve Moeller. He still lives. I met him at a conference, and when he just started working on MATLAB, they made a movie about the singular value decomposition. So in the picture here you see a screenshot of that movie, and this was actually used in the Star Trek movie, the original feature film, so the long film, not the television series, but the first film that you could see in the cinema on Star Trek. There have been many more, of course. This footage was used on the bridge of the Starship Enterprise. So Spock, who is a science officer, he is running some simulations, or at least that's the idea, and behind him you see the visualization in the movie on the screen. So let's watch this short movie that's also available on YouTube. The YouTube link is here, and also Cleve Moeller, he writes his Cleve's Maths Corner on the website from MathWorks, which is the company behind MATLAB, and he also wrote a little article about that. So first of all, let's watch this movie.
To a mathematician, a matrix is a table of numbers which describes the relationships between the components of various kinds of systems. The system might be a bridge, an electrical circuit, a nuclear power reactor, or a sociological group. Each of the components of the system, the bridge struts, the resistors and capacitors, the neutrons, or the individual people, interact with the other components. The matrix elements represent the intensities of all these interactions. Analysis of the system using matrix techniques allows one to predict the effect of individual interactions on the overall system. Oscillations may be generated. Matrix analysis can describe the frequency and magnitude of such oscillations. This bridge near Tacoma, Washington, was designed and built before the effect of such interactions could be completely analyzed. The wind has reinforced some undesirable oscillations with unfortunate results. Modern computers are particularly well suited to solving problems involving large matrices. The designer of a system can obtain accurate predictions about the reaction of his system to external forces. The computer is used to simplify the matrix so that most of the entries will be zeros. One method is known as the singular value decomposition. The original matrix is represented as the product of three matrices. In the second of these matrices, the only non-zero elements lie on the diagonal. These elements, the singular values of the matrix, determine the frequencies of oscillation of the original system. The other two matrices must preserve the properties of the original matrix, so they are orthogonal matrices. Each is the product of elementary matrices which affect only two rows or columns. Scientists at Los Alamos Scientific Laboratory have been studying methods for the accurate and efficient calculation of the singular value decomposition and of describing to computer users how the computation is carried out. In this three-dimensional representation of a small matrix, each pyramid depicts the magnitude of a single matrix element. The diagonal of the matrix runs from the upper left to the lower right. Orthogonal transformations will be used to introduce zeros into the matrix. The initial transformations put zeros into the first row and then the first column. Each transformation affects two other columns or rows shown here in blue. Later transformations introduce zeros into later rows and columns, while preserving the zeros already obtained. It is not possible to annihilate all the off-diagonal elements in a column, so this first stage produces a matrix with non-zero elements directly below the diagonal, as well as those on the diagonal. This film is produced by exposing a single frame each time a matrix element is altered, to illustrate roughly the computer time actually required for various phases of the computation. The elements shown in red are involved in auxiliary calculations which require time, but which do not directly alter any elements. As more zeros are introduced, the rows and columns become shorter, and each transformation requires less time. The second stage of the calculation is a repetitive or iterative process which reduces the size of the remaining off-diagonal elements, but does not zero them in a single step. During the process, new elements, shown in red, are temporarily introduced into the matrix. The calculations now being shown are primarily intended to reduce the size of the off-diagonal element at the lower right-hand corner. Once an off-diagonal element has reached a negligible magnitude, it is set to zero. The computation of the corresponding diagonal element is then complete, and the resulting singular value is shown in blue. During these iterations, most of the other off-diagonal elements are also being reduced in size, although not as rapidly. A few of them will occasionally increase in size. This makes theoretical analysis of the method difficult, but does not seriously impair its overall effectiveness. Since elements are being depicted according to logarithmic scale, the off-diagonal elements we see are actually quite small by this time. The transformations are still changing the diagonal elements, but the changes are not visible on this scale. Once a few of the singular values have been obtained, the off-diagonal elements have become so small that each of the remaining singular values is obtained with a single iteration. The final diagonal matrix, together with the two transforming matrices which produced it, then provide the basis for a complete analysis of the original matrix and the system which it models.
So what we have seen just now in this little movie is a visualization of computing the singular value decomposition. I'm not sure if you noticed, but at the very start of the little movie clip, they show a matrix, and you know, a matrix is a square or a rectangle with numbers, but there they show them as hexagons, so that's quite interesting. Apparently the movie was made by people who were non-mathematicians. But we also see the correct formula for the singular value decomposition. So you decompose a matrix A as a product of three other matrices, U, sigma, and V transpose. And sigma is diagonal, and on the diagonal it has the singular values. And both U and V are square matrices, and they're orthogonal matrices. So that means they're rotations, reflections. They're the type of matrices that correspond to linear maps who do not change the length of a vector. So let's see here. Suppose that our matrix has size m times n. So m is the number of rows and n is the number of columns. And we're going to assume here that it has more rows than columns. Then sigma has the same size. And it's a diagonal matrix, so it's mostly zeros only on the main diagonal, so starting from the top left, and then the 1, 1, 2, 2, 3, 3 elements, and so on. They are non-zero, and the rest of this matrix is whole zero. So it's a kind of generalization of the diagonal matrices, as you may have seen before. Usually they're square, but you can also do that for rectangles. In the U matrix are the eigenvectors of A transpose, and then a normalized version of them. So they all have length 1. Every column of this U matrix is a vector of length 1. And if you pick 2 columns in U and you compute a dot product, you will find 0, meaning that all the columns, all different columns, are orthogonal to each other. And for V transpose, something similar. V transpose, of course, the transpose of a matrix V, and V has the eigenvectors of A transpose A, and we will also assume that they form a normalized system and all vectors are orthogonal, so an orthonormal system of vectors. So as an example, this is a matrix with 4 rows, 2 columns, and you can write it, I'm not going to do the computations here, but you can write it as an orthogonal matrix. This thing is orthogonal. All columns have length 1. If you take 2 columns and compute a dot product, you will find 0. Same holds here. This is the V transpose matrix. And this thing here is the diagonal matrix, sigma. And apparently the singular values of this matrix A are square root of 10 and square root of 5. Now I'm going to write it a little bit differently as a kind of transition to what I want to show next. I'm going to write this U matrix here in terms of its columns. So it has 4 columns, U1, U2, U3, and U4. This thing I'm going to write in terms of its rows. So here we have first row and second row. And then I write sigma 1, sigma 2 for the singular values, and that's just to make the formula look a bit more general. So next, if you compute the product of these two, you see that you get what it says in the line below. And if you do the matrix multiplication that it says here, then you see that you get the sum of 2 terms. Each of these terms is a matrix, because if you multiply, this is a column vector, this is a row vector. If you multiply them, you get an n times n matrix. And it is a rank 1 matrix, meaning basically you take the first row of that matrix and then all other rows are some multiple of the first row. It has rank 1. The column rank, there is only 1 independent row, 1 independent column here. Now, you can generalize this a little bit. So here for a general matrix A, I can also write it as U times sigma times V transpose. And now we've got M columns, and here we have N rows. And this thing has the same size as your original matrix. And now you see that you can write it as a sum of N rank 1 matrices. And the idea is that here we have an equal sign, so this holds. So apparently we can write any matrix as a sum of rank 1 matrices. And also we always assume that the singular values are ordered in size. So that means that sigma 1 is the biggest, and then sigma 2, and finally sigma n is the smallest singular value. Now, if you take only, say, the first 2 or the first 3 or the first 4 terms, then you get an approximation to the matrix. Now, how can we use that for face recognition? That seems to be a long way off. The idea is something that they call eigenfaces. So what we do is we take all the photos of person 1 in our training set. And what we do, they are vectors. So we build a matrix out of these vectors. So we have a matrix, and this here is the number of pixels. And this is the number of faces that we have. So here we have 10 faces. Every face is a vector of length 77,000. I place them next to each other, and like this I build a matrix. The next thing I do is I compute the singular value decomposition using some software package. And now the idea is that if you look at the columns of this U matrix here, that they extract the important information from the matrix. So in this situation, the characteristics of this person's face. And you see that the first column of the U matrix, the first eigenface, looks very, very much like the average. If you would compare to the average face, you would see that they are identical. And then the next column of U and the third column of U, they provide extra information. And because you can write your matrix as a sum of all these rank 1 matrices, and they are listed in importance, you can extract some information and throw away the stuff that you do not need by using the first little r columns in this expansion, in the sum. So I'm also going to do the same for the other persons. And now my idea is the following for a face recognition algorithm. So what I did here, I've now made a kind of clouds like you see for the number 4 here. That's person number 4, eigenfaces space. So you take, for instance, the first 3 eigenfaces, the first 3 columns of the U matrix for person 4. I grab all the photos in the known training set from person 4, put them in a matrix, compute singular value decomposition, look at the U matrix and take the first 3 columns. I can form all linear combinations of them, that's a vector space, and this subspace here is what I mean with this cloud. And now what I'm going to do is, if you give me an unknown photo and you would like me to classify it, I'm going to write this unknown photo, this cross here, in terms of the eigenfaces of all the 15 people. And next I'm going to check which one is closest, and I'm going to label my unknown photo as that person. So in an algorithm, what do? We choose some number, the number of eigenfaces per person that we would like to use. I write the unknown photo, so the red cross here, as the best combination of the first r eigenfaces of person 1 and then person 2, 3 and so on. So you can do that. I do not really give the details here, but you can do that. And then you find the nearest combination, so the best combination. And if that is the combination from the eigenface of person P, I'm going to label my photo as such. So how does that work? Before I go to the numerical results, just one statement. We've seen the very simple and naive algorithms, which can be quite good, but they take a lot of computational effort. And here we can do some of the work in advance. So finding all these eigenfaces, you can do that once. And next, for every unknown photo, you can use what you've already computed. And here, what is nice is that there's also this parameter little r here. So the more of these eigenfaces you use, the better it will work, but the more expensive it is. So you can trade accuracy and efficiency of your algorithm. If you want very fast recognition, you pick a small number for little r here. If you want very accurate recognition, you pick a larger number. So you can make a decision here. You can balance it. So if you do that, so I've implemented that, and if you take 1 or 2 of the eigenfaces, then you get an 87% rate of correctly identified photos. If you pick r to be bigger or equal 3, then everyone will be recognized correctly. And just to see when does it go wrong, well, in the same cases that the average person would go wrong. So this is the unknown photo here, and this is this person written in terms of 2 of his own eigenfaces, and this is if you would write his photo in terms of the eigenfaces of the person on this photo. So you see that it doesn't work well for this photo. The costs here, well, you have to compute all these eigenfaces, but the trade-off is that you only have to do it once. Next, I have to write my unknown photo as a combination of eigenfaces, and that 15 times because eigenfaces of all the different people. And then I have to compute the distances to these combinations of eigenfaces. So also 15 distances. So a bit more work than the average faces, but here we can also make it more accurate than there. So finally, a bit how does it work in practice? So Google FaceNet is one of the best algorithms we have for face recognition. And the way it works, so there is a paper, you can access it here. So I put the link here and you can download it for free. It's open access. And what they say is that they map a photo to a vector of only 128 bytes. So that's very, very little information, very few information. And they say that the neural network that does that, so this uses neural networks, which is called FaceNet, it learns a mapping from face to a compact Euclidean space, so to a vector, and apparently the distances in this Euclidean space, so in Rn, in R128 apparently, is a good measure of phase similarity, so are people alike or not. Then also Apple, when it introduced its iPhone X, there was also a system for face recognition in there. They do a little bit more, and I also wanted to point that out. So what the iPhone does, since the iPhone X, is that it projects infrared dots on your face and then does a 3D scan. So what they do is they don't use a 2D image, but they have depth information too. Because of presenting these dots, they've got depth information on your face, and that helps. And then if you look at the public relation materials, they say that they map it to a math representation, which is undoubtedly a vector. And here it is a little bit different, because what your iPhone does is compare the scanned image to an image it had before, and then it checks whether you are the person that can unlock the iPhone or not. So, a conclusion. Apparently, mathematics can help to teach a computer to recognize faces, and the background there is that you can represent a photo with vectors, and once you have vectors, you can do all the linear algebra and numerical linear algebra that you would like to do. And the singular value decomposition finds main features in given data. So if you want to have more information, if you would like to read more about this, my presentation from Nationale Wiskundedagen, National Mathematics Days, is on my website, and you can click there. There you will also find the workshop that we have done with the celebrities. You can also read Esme Stein's thesis for her bachelor project. It's written in Dutch, but it's publicly accessible from the library of TUE. And there is a very nice book called Matrix Methods in Data Mining and Pattern Recognition by Lars Elden. And he spent a chapter also on face recognition and uses not the usual singular value decomposition, but a tensor singular value decomposition. And a tensor is something like a 3D matrix. So a matrix is a rectangle. If you add one more dimension, you get a tensor. And what he uses there is not only faces, but he looks at, for instance, emotions of the faces. Or you've seen that I had pictures taken from front, right, center, and so on, or happy faces, and you could use that extra information. And then the Yale Face database, if you want to check your own face recognition, you can download that too. So I hope you like this. I think it's a very interesting application of singular value decomposition, maybe also an unexpected one, since normally you don't think of photos as vectors. And this concludes the presentation. Thanks for being with me here.